WhatsApp group. Okay, so let's start with the optical system of the eye, or our first lecture in the human optics. So, our basic principle, or our main purpose for human optics, is to calculate the power of the human eye. So, calculation of the power of the human eye is the basis of all optical correction and surgical correction of the refractive error of the eye. So, if you wonder how we can calculate the glasses prescription for myopia or hypermetropia or astigmatism, or how can we calculate the amount of refractive error needed to be calculated by the LASIK machine, so this all has a one fundamental rule, or one basic rule. It is the knowing how much is the power of the eye. So as we mentioned in the first early lectures, that the power of the eye is calculated in, or the power of any refractive surface is calculated in the term of diopters. So the diopter is the ability of a refractive surface to converge or diverge ray, making it to a focus placed at 1 meter from the refracting surface. So how much is the diopteric value of the eye? How can we calculate it? This can be done by different means. The first one is by calculation of the power of each surface separately, and the second is by calculation of the power using the Gauss and Listing theory, this theory that we mentioned in the previous lecture, which is the thick lens formula, in which if there are different refracting surfaces that are centered on a common axis, they are called a compound homocentric system. And by knowing the rules of Gauss and Listing theory, we can calculate if we assume that the eye is considered as a thick lens. Or the third method is called the Donder's reduced eye. So let's start first with the calculation of each refracting surface power separately. So basically, let's know some definitions, and let's identify what are the main refracting surfaces in the eye. So we have three major refracting surfaces in the eye. The first one will be the anterior corneal surface, and then the anterior lens surface, and the posterior lens surface. The effect of the posterior corneal surface on the power of the eye is very minimal. And by knowing that these are the main refracting surfaces, we need to know what is the radius of curvature. So the radius of curvature, as we mentioned in the early lectures, is the distance between the center of curvature of any spherical lens, or any sphere, and any point at the surface of this sphere. So if we have a large sphere, so this lens has this large lens has large radius of curvature. However, the lens itself has minimal curvature, so they are less curved. On the other hand, if we have a small sphere, it has a smaller radius of curvature, but the lens itself is more curved. So the radius of curvature and the power of the curvature of the lens are both inversely proportionate to each other. Again, if we have a lens that has a high power, it will have a smaller radius of curvature. If we have a lens of a small power or a small curvature, will have larger radius of curvature. So based on how much each surface of the eye is curved, the radii of curvature of these surfaces are calculated. So the surface, or the radius of curvature of anterior corneal surface, it is 7.7 millimeter. However, the posterior corneal surface is more curved than the anterior corneal surface. That's why the radius of curvature of the posterior corneal surface is less than the radius of curvature of the anterior corneal surface. Also, the radius of curvature of the anterior lens surface is 10 millimeter, but since it is less curved than the posterior lens surface, then the radius of curvature of the lens surface is smaller than the radius of curvature of the anterior lens surface. So again, the anterior corneal surface is more curved, but less curved, but has larger radius of curvature than the posterior corneal surface. And again, the anterior lens surface is less curved and have larger radius of curvature than the posterior corneal surface. The distance also of each refracting surface from the anterior corneal surface is very important in order to calculate the power of the eye. So the anterior corneal surface is considered like our start point. So here, the anterior corneal surface, the distance is 0 since this is a start. And when we reach the posterior corneal surface, we traveled a distance of 0.5 millimeters or 500 microns, which is basically the thickness of the center of the cornea. Then the distance of the anterior lens surface, it is 3.5 millimeters, which is basically the depth of the anterior chamber. If we add the thickness of the lens to the depth of the anterior chamber, then we will get the posterior lens surface, which will be situated about 7.2 millimeters behind the anterior surface of the cornea. So here we can see again in the this section, we can consider that the anterior corneal surface is the 0 point. So the posterior corneal surface is 0.5. The anterior lens surface is 3.5 millimeters behind the anterior surface of the cornea, and the posterior lens surface is 7.2 millimeters. The refractive indices of the different ocular media should also be taken into consideration when determining the refractive power of the eye. So the cornea has a refractive index of 1.376. The aqueous and the vitreous have the same refractive index of 1.336. The lens itself has is composed of different materials of different refractive indices. So the nucleus has a larger refractive index of 1.4, while the cortex has less refractive index of 1.3. So as we said, we need to know the refractive power of the eye by calculating the refractive power of each refracting surface separately. So we have two main refracting surfaces, which are the cornea and the lens. So we need to calculate the power of each one of them separately. So let's start by the cornea. So we have a principle that the power of any refracting surface will be equal the refractive index of the material or the medium next to this refractive material minus the refractive index of the material before this refracting surface divided on the radius of curvature of this refracting surface. So if we take the cornea as an example, so the refracting power of the anterior corneal surface will be equal the refractive index of the cornea, which is N2, as we can see that when the air is hitting the air cornea interface, it will pass into the air first, so it will be N1, and the cornea second, so it will be N2. So N2 will be equal to the refractive index of the cornea, which will be 1.376, while N1 will be equal to the refractive index of the air, which will be 1, divided over the radius of curvature of the anterior corneal surface, which is 7.8 millimeter. And since this rule is only on meter, so we convert 7.8 millimeter to the metric value, which will be 0.0078. And by calculation of this formula, it will end up with a power of the anterior surface of the cornea with 48.8 diopters. So, but the cornea doesn't have only an anterior surface, but it has also a posterior surface. So this needs to be calculated as well. The power of the posterior corneal surface will follow the same rule. So since the light rays pass from the cornea to the aqueous, so N2 will be aqueous, so it will be 1.336 minus the refractive index of the cornea, which will be 1.376, divided on the radius of curvature of the posterior corneal surface. And since the refractive index of the cornea is larger than the refractive index of the aqueous, this will lead to that the net result will be in the minus value. So the power of the corneal surface or the posterior corneal surface will be equal to minus 5.8 diopters. And this is logic because the posterior corneal surface acts as a concave lens, not a convex lens. This is due to its configuration. So if we need to know the refractive power of the whole cornea, this will be the summation of the power of anterior corneal surface and the power of posterior corneal surface. So the net result will be the plus P1 plus P2, or the power of the anterior corneal surface plus the power of the posterior corneal surface, which will be equal 43 diopters. So this is the regular or the average power of the human cornea. It is 43 diopters. And from this, another formula is used also for determining the radius of curvature or the focal length. So as we know, any lens has a focal length, and this can be either f1 or f2, as we mentioned in the previous lecture. So f1 of the cornea will be equal the f is equal the refractive index of the first medium divided multiplied by the radius of curvature divided over the radius of the refractive index of the second medium minus the refractive index of the first medium. So if we follow this rule for the f1 of the cornea, this will be equal 1, which is the refractive index of air, multiplied by 8, which is average radius of curvature of the cornea, divided by into minus n1, and this will be equal to 24.5 millimeters. So f1 of the cornea is 24.5 millimeters. So if we have a parallel rays which is emerging from the eye, and they will come to a focus at, if we have only the cornea as a refracting surface, then they will come to a focus at a distance of 24.5 millimeter in front of the eye. So this is if the eye has only cornea and there is no lens. So we can assume that this formula is valid for aphakia. F2 will follow the same principle. So it will be the refractive index of N1, which is the cornea, multiplied by the radius of curvature divided over the radius of curvature of the N2 minus N1, and then this will be 32.5 millimeters. So if we have a parallel rays that are falling over the cornea, they will come to a focus at a distance of 32.5 millimeters behind the cornea, so they will be situated even behind the eye. So this will lead to, this is if the eye doesn't have a lens, so this eye will suffer from severe hypermetropia. You may notice that the f1 is not equal to f2. So why does this occur? So is this, if this a lens, why does the f1 is not equal to the f2 behind it? We have also mentioned this in the previous lecture. This is because the refractive indices are different in both sides of the cornea. So in front of the cornea there will be air, which has a refractive index of 1, and behind the cornea will be the aqueous and the vitreous, which will be having the refractive index of 1.336. So since that there is a difference in both refractive indices, hence there will be a difference in the f1 and f2. And the clinical application of this, why do we see the objects blurred while we are in the water? So if we are swimming in like a swimming pool like this, and we are opening our eyes, we can see that objects are blurred. So this is because we are not used to see within the air, within the water. The water has a very close refractive index to that of the aqueous. So there is no air corneal interface to bend the light rays in order to see clearly. So the difference between the refractive index between the cornea and the water is only 0.04. So this is the refractive index of the cornea, 1.3, and the water is 1.336, which is similar to that of the aqueous, so that we don't see clearly. However, if we put goggles or swimming goggles, and now will be air in front of the eyes, now we can see clearly. This is because the air corneal interface is now of the normal value, or the light rays will be bent over the normal value, and thus we can see a clear image in our retina. So since we calculated the power of the cornea, we knew that the formulas that are used for calculation of the power of the cornea, the formulas that are used for calculation of the power of lenses are not of importance to us. But we need to know that the power of the lens is different according it is intraocular or in vivo or extraocular or in vitro. This is because of the effect of zonule. So the zonule act as flattening of the lens. This flattening will cause the refractive power of the eye or of the lens, or the crystalline lens will decrease dramatically. So it will be only plus 17 diopters. However, if it is extraocular, so the lens will assume a globular shape and become more curved, leading to more power. So it will be about plus 63 diopters outside the eye. And in such conditions, whether it is inside the eye or outside the eye, the f1 and f2 will be equal. So it will be 56 millimeters. And this is because that the refractive indices in front and behind, whether they are inside or outside the eye, will be the same. So in case of the inside the eye, the refractive index of the aqueous will be the same to that of the vitreous. That's why the refractive index of the lens will be the same, or the f1 and f2 will be equal. So we now know the refractive power of the cornea and the refractive power, which will be about 43 diopters, and we have the refractive power of the lens, which will be average of 17 diopters. So the average of the human eye power will be 16 diopters. So this will be the first method to determine or to calculate the power of the eye. Is everything clear up till now? Okay. Okay, so let's now move to the next method for determining the power of the eye. This method was discovered by a scientist called Goldstrand. And as far as I'm concerned, the Goldstrand is the only ophthalmologist that obtained the Nobel Prize. And he obtained the Nobel Prize because of this discovery, which is that making a scheme for the eye based on the Gaussian and listing theory that has been able to calculate the power of the eye, so that that this will be the, as we said, the basis of all optical and surgical correction of refractive error. So let's see how did Goldstrand discovered or formulated his schematic eye formula. The base of the Goldstrand discovery was the Gaussian theory. So Gaussian theory that we mentioned the last lecture is the theory of a thick lens, or a thick lens formula. If we have a different refracting surfaces that are centered on a common axis, this is considered as a thick lens. So if we have a coaxial spherical refracting surfaces, they can be considered a thick lens, and the same rule here applies to the eye. So Goldstrand thought that the eye can have the same principle like the Gaussian theory, as the eye is also having different refracting surfaces that are centered behind each other, like the cornea and the lens. So why not we apply the compound homocentric system over the eye? So if we have different lenses, as we said in the last lecture, they are having the same optical axis, this can be considered as a thick lens. So Goldstrand said that the refracting system of the eye is expressed on cardinal points, measured in millimeters behind the anterior corneal surface. So what the Gaussian and listing theory of the thick lens said that if we have a thick lens, we have 6 cardinal points. These 6 cardinal points are 2 focal points and 2 nodal points and 2 principal points. So this is what the Gauss and listing said in the thick lens formula. So what Goldstrand said that, okay, we can use the same system for applying on the eye. So in the eye, we will use the 2 focal length or 2 focal points and 2 nodal points and 2 principal points. So according to the Goldstrand, where do these points located? According to the Goldstrand schematic I, the first principal point, or P1, is located about 1.35 millimeters behind the anterior corneal surface. So all these measures are measured from the anterior corneal surface. The second principal point is present 1.6 millimeters. The first nodal point is 7.08 millimeters. The second nodal point is 7.33 millimeters. The first focal point is the only point which is located outside the anterior corneal surface. So it is located in the air. That's why it is in the minus value. So it is minus 15.7 millimeters. The second focal point is F2, which is 24.4 millimeters, which is the same axial length of normal average human eye. By calculation or different calculations, the Goldstrand reached that the refractive power of the eye will be equal 58.84 diopters. So let's see this in action. This is a schematic eye as drawn by the Goldstrand. So all measures are taken from the anterior corneal surface. So we have the first located about 1.35 millimeters in the aqueous, and the P2 or the principal point 2 is located 1.6 millimeters again inside the aqueous. The N1 and the N2 are straddling the posterior corneal surface. Just hold on. Okay, so the N1 and the N2 are straddling the posterior lens surface. So N1 is in front of the posterior lens surface, while N2 is behind the posterior lens surface. The F1 is in the minus value because we measure from the anterior corneal surface. So we are now moving from the right to the left. So it is minus 15.7 millimeters, while the F2 is measured from the anterior corneal surface will be 24.4 millimeters. So it will be located on the retina. So this will be the like principally that this is the axial length of the eye. So based on the calculations that we don't need to it is not our duty to know any of these calculations, the Goldstrand reached that the power of the eye will be equal 58.84 diopters. So you note that the nodal points at which the light rays pass undeviated, they are removed from the principal points. So you are used to that to see that the nodal point will be coinciding with the principal points. And why we separate this? Because this is there are different refractive indices in front of it and behind it, and also we have mentioned this in the previous lectures. So as you can see that these lectures are from now, and then the coming lectures will be based on what we have studied and what we have discussed in the previous lectures. So this is because the refractive media on each side of the refracting system of the eye are different. So the refractive index of the air is equal 1, while the refractive index of the vitreous is 1.336. Also, these are common areas in the asking in the MCQ exams, that the nodal points are straddling the posterior pole of the crystalline lens. So we have one nodal point in front of the posterior lens surface, and the other will be behind the posterior lens surface. The pupil of the eye allow only small amount of light rays to enter the eye, and the paraxial rays will be refracted and concentrated through the nodal points and the adjacent posterior lens surface. So for any surface or any light ray will pass inside the eye, it should pass into the nodal point. The light will it will pass Only the light rays that will pass into the nodal point will pass undeviated. And since then, if we have a small posterior polar cataract or posterior subcapsular cataract, and these are in close proximity to the nodal point. And that's why if we have such opacities, or if a patient have such opacities, then they are will be very visually significant because they are close to the nodal point. So this is how we can correlate the optical principles to the clinical life. If we have central posterior subcapsular cataract or central posterior polar cataract, this will be visually significant and obscure the central vision for the patient because they are close to the nodal point.